Okay, so it's 10:15. It's time to start. So first of all, thank you everybody for being here. Also, people home from Leuven and in Edinburgh. So this is the second workshop we managed to organize thanks to the support of our Une Europa project. It's the title. You see, Tensor-based Optimal Control Approaches for Deep Learning. And I will start with the team. It's us. This doesn't work. So this Nick from Leuven, Jemima from Edinburgh, and from Bologna. So we must thank the Polish National Agency for Academic Exchange that basically gave us the money. And this is I don't know how many of you know about Une Europa, but it's a very special call. It's called Une Europa digitalized, because basically even like the topics of the projects that people could submit, basically they all belong to the spatial area, I would say, like digital technologies for societies, more or less. So Une Europa is a big consortium of these universities right now. I think now that we also have the University of Zurich that's joined in Europa. So like many universities in Europe. And basically the aim of this consortium is like to try to improve networking between these universities, going from teaching to research to whatever you want. And this is the point of this Une Europa SIP funding, to try to like gather people together and have ideas and start working together. And this is basically what we did. As I said, the topics of this call were about digital technologies. And so here I just copy paste the call. And we focus on this here. So like new algorithm to aid decision making. And in particular, we're trying to, I would say, speed up the training phase of deep learning techniques. And I think Nick would like to tell us a few words about what we've done so far, because this is a very short project. So it started like last February, it goes to the next September, so we don't have so much time to try to have some kind of like research outcomes, but it's what we did so far.
All right, thank you, Davide, for the introduction of the Une Europa network. So what we've been doing is work on some alternative machine learning models inspired by deep learning. And so the idea here is that rather than doing this neural network, we're thinking about doing something related to ODE solving, because of course, from the applied mathematics community, there's a lot of insight into solving ODEs. And there has been some recent research that interprets some types of deep learning as a kind of like a first order approximation of solving an ODE, like a forward Euler method. And so what you can see here on the slide is our proposed architecture that we've been experimenting with. So the idea is you give me some input, which could be either raw input, or it could be something after you've already extracted some features. And then essentially what we do with this, as is shown over here. So there's this jump in evolution space. Basically, we're doing something that neural networks do as well. Linear transformation and then a non-linearity. This is the first step that we do. We apply this to the raw input. And this is used essentially to define an ODE. And then this ODE is solved using any method we like in principle. And then at the end, so it's kind of like an evolution process taking place in an auxiliary space, trying to figure out somehow what's going on with your problem. And then finally, when you're in the evolution space, you still need to go back to the space where you want to perform the classification. And again, here you could either use existing machine learning technology, so view this pipeline as a way to extract more features to make the classification easier, or as in the current setup, as we have been doing, to immediately perform the classification. And again, this last part over here, the last layer, if you will, is again of the same type. So it's again linear map and then some non-linearity applied. All right. So how do we evolve? So the idea is some ODE-like evolution process. So initially we were thinking about evolving PDFs, evolving a probability density function, which should somehow encode, you know, like if you want to perform a classification problem and you use one hot encoding, you can interpret this as probabilities that your input belongs to a certain class. So this was the rationale for using this setup, and the idea would be to evolve the PDF using some type of ODE. And so the way the ODE is constructed, currently it's a linear ODE, as you can see over here. The initial condition is determined by, again, some type of, you know, one layer of a neural network in some sense, linearity and non-linearity. And then the way that the evolution progresses here, so the linearity is given over here. So essentially it's a tensor, and to this tensor you apply on, so you can imagine this as a box of numbers, and we need to get some type of matrix. So we contract the tensor, we make a linear combination of matrices, and this gives you one matrix. And this is what you need to define this linear ODE, of course. And now the way that the matrix is constructed, again, this is where we use some form of nonlinearity. So this is the first part over here. Again, you can see linear map and then a nonlinearity applied. Okay, and so how do we do the training? Well, actually, a similar setup as in deep learning, where you say, okay, you give me a bunch of input-output pairs, and I'm basically going to try to match the predictions of the models to the given data, of course. Right? So what we've been using right now is just deterministic methods. So usually people for training deep learning models, they would use something like a stochastic gradient descent method, potentially or generally with the momentum terms. But here we're just using deterministic optimization. So we're using right now quasi-Newton method in MATLAB, just admin unconstrained basically. Second thing that is slightly different from what I explained before is that this tensor, so where we combine these matrices, we impose a very special structure. So basically, we are imposing a low-rank structure, which actually allows us to solve the ODE in a very efficient manner. And I believe this is not on our slides. Well, it's the tensor structure is over here, and essentially it allows us to kind of diagonalize the problem. So the linear ODE really becomes a diagonal ODE, so like a separated ODE, which then consists of separate evolution processes, which you can solve with the exponential method very efficiently. So you don't need to compute a matrix exponentially, you need to exponentiate some entries in a diagonal matrix. All right, and then I think we have some numerical results that Jemima is going to present. Some preliminary results, of course.
Yeah, so we wanted to kind of test our method on some kind of things that were easy to visualize and understand what the results were. So we came up with these kind of case studies that we present on in the following slide. We're obviously looking at more complicated problems with, at the moment, but these are the ones we have results for at the moment. So basically what we have is we have two inputs, an X and a Y. And then we're trying to recover some predetermined domain. So we've got a couple of different examples here. And so on the pictures, what we have is that the circles of different colors will be our training pairs. So we'll have an X and a Y coordinate, and then we'll say, is it in class 1, which is this, in this case, the top right-hand corner, or is it in class 2, which is the bottom L shape. And then we apply the method Nick just outlined to these pairs. Get an approach that allows us to predict for new information, and then the blue crosses or different color crosses, we then because we have this grid-like structure for each point in the domain, we then apply the model that we've learned and then assess whether it's in class 1 or in class 2. So you can see here what we'd like is all the blue crosses to be in this bottom L and none to be in the right corner. We can see we've done quite well, but in this corner here, we've got some points that are misclassified and some points on the boundary are not quite classified. So for these, as Nick said, and David, I think we have a lot of parameters we can tune and play with. For this example, these examples, we're using similar parameters. So in particular, probably of interest is that we're using the same non-linearity at each of the levels. And that we found that quite well in this example. This is really this most simple example of we have two classes, can we distinguish between them? Kind of the second most obvious example was, well, we have 3, can we distinguish between those? And we see here that we could do that quite well. Again, we have some problems on the boundaries, but that's maybe to be expected. One we found quite interesting was this kind of bisection of our domain with this curve. And again, we do well kind of far away from the boundaries at interface, but we struggle on this is quite typical, I think. And our final example is this kind of concentric circle example. So here we're using a different nonlinear term, leaky value, which is quite typical for these neural network approaches. We can see that again, we have some places on these boundaries, but we're doing quite well at distinguishing between these 3 different classes here. And so obviously the aim, this is quite a simple problem, we only have a vector of 2 inputs. Really, we might have many, many variables. So at the moment, we're looking at examples from this MNES data set, which has the input dimension is 782, I think, and then we have 10 classes. So that's kind of where we're at the moment. So that's the preliminary results, and now we're going to present what's going to happen the rest of the morning.
Yeah. So, of course, you can find us. So we have a website here if you want to keep in touch and have a look at what we do. We have a Twitter account. We have a YouTube channel where we're going to post the recordings from today, and also we had already the recording from last workshop when we were in Edinburgh, and Margarita talked about some optimization procedures. And next visiting will be in September in Leuven. We'll have another workshop there, and so you can also have a look at those recordings if you're interested. And today, so the first speaker, this is the outline of what's going to happen today. We have 3 talks with a break in between. We're going to have some coffee and some snacks. And the stage is of the first speaker of the day.
All right. So our first speaker for today will be Brecht Evens from KU Leuven. So Brecht is currently a PhD student with Panos Patrinos, who is at the Department of Electrical Engineering. Also, Brecht is at the Department of Electrical Engineering. And they've been working on some very interesting methods for kind of reinterpreting deep learning or alternative ways of viewing this optimization problem, which are in fact very much related to the topic of this workshop. So let me stop the share here. And then ask Brecht to share his slides.
Yes.
Okay, so if there are questions from the room, of course, we can take them. If there are questions on Zoom, please type them in the chat or indicate in the chat that you would like to ask a question, then we can try to ask the question here for everyone in the room as well. Okay, so we can see the slides from Brecht. This looks good. Can we hear you?
Yes.
Perfect.
Can you hear me?
All right, great. So the floor is yours. Go ahead.
Yes, one more question. Can you see my cursor as well?
Yes.
Okay, great. And I can point some things. Okay, so in this presentation, I'm going to talk about neural network training and how it can be interpreted as an optimal control problem. And then once this interpretation has been settled, then I will show you how you can use an augmented Lagrangian approach to solve the subproblems that emerge in neural network training. So first, I will talk about how you can interpret neural networks as an optimal control problem, and then introduce this augmented Lagrangian method framework for equality constrained NLPs, which is the problem which we'll end up with. Then I will talk about how you can solve the Lagrangian subproblems, which will emerge in this framework. And finally, I will give some numerical results and a short conclusion. So first, neural network training as an optimal control problem. I'm going to start with some very simple slides, like what is a neural network? Simply, we have our input layers, our hidden layers, and our output layers. And at each layer, you have these X variables, which are activations at each layer, and they are interconnected with the weights. So as mentioned in the previous presentation as well, you simply have this nonlinearity or activation functions coupled with a linear mapping, which couples this activation at the next layer with the activation at the previous layer. So in a general neural network, a classical neural network, given some input to the network simply predicts like a combination of linear mappings and nonlinear activation functions in a sequence. So you have this large concatenation of all these functions and linear mappings. Now, what is the goal in neural network training? Well, it's to learn the underlying mapping from input-output pairs, right? We want to, given some inputs, want to, as accurately as possible, predict the outputs given data. And here the performance is evaluated through some loss function, most commonly mean squared error, cross entropy, hinge loss, etc. And then to do this in machine learning, usually first order methods are used for training, like simple gradient descent, stochastic gradient descent, etc., where the gradient is obtained using backpropagation. But it has been noticed that this can cause some kind of issues because we have this very challenging, highly non-convex training task, and we are using a simple gradient method to solve the problems. And the question is, does this suffice, and why wouldn't it? Because you have a lot of local minima, for example, where your gradient method can get stuck. And furthermore, you have a so-called vanishing or exploding gradient effect in neural networks. And now, what does this mean, this vanishing and exploding gradient phenomenon? Well, I've designed a little simple visualization of this. So we're going to consider a very simple neural network with 6 hidden layers. And each layer has single neurons and all weights are equal. And we have linear activation functions. So it's really a trivial network with an MSE cost. So you have this simple, just linear mappings to the power 7 times the input should match the output of the network. So if you take A as 1 and B as 1, you get this cost function actually. And this is quite surprising. It's such a simple network, but the problem is if you apply gradient descent and you start in this region here for the weights between -0.5 and 0.5, your gradient is almost 0. So you have very little information on the error to converge towards your optimal weight. So if you apply gradient descent in this case, you would need actually quite a large step size, for example, and then you would be able to slowly converge towards the optimum, which of course is 1, right? But the issue with this is, well, in these other regions, what happens here? Well, in these regions, our gradient completely explodes. It becomes very large. So in this region, you would need a very small step size. So this is an issue which happens even in the most simple neural networks, and it happens in big ones as well. And usually people just try to tune this hyperparameter manually, but perhaps there are more sophisticated ways of dealing with this. And this is the main idea of this work. Well, the key insight here, which I'm going to apply, is to view the training task as an optimal control problem. Because we had these activations at each hidden layer. And I'm going to look at them from the control spec perspective, because this is also, I mean, I'm working at Panos' group, which focuses on control techniques mainly. So this is like making a bridge between our works. In this context, I'm going to consider the activation at each hidden layer as a state vector. And the state vector is influenced through the controls, which are the network weights. And their activation functions then represent the dynamics of the system, basically. So in some sense, it's equivalent to controlling an autonomous vehicle, for example, n time steps into the future. For example, for a vehicle, you have a state vector, which is the position and the velocities, etc. And you want to control it by applying accelerations or steering angles. So this would be your controls. And then the activation functions are like the dynamics of the vehicle, how it reacts to applying inputs. So these problems are completely equivalent, but this is something which is kind of underexploited in current literature. And I think that these communities could benefit from learning from each other. Well, under this interpretation, then backpropagation in some sense amounts to the single shooting approach from optimal control, where the state variables are eliminated, they are not taken into account, and you simply propagate the nonlinearities through the network so that you end up with a very nonlinear and non-convex cost function for which gradient descent is then used. Well, in the control community, often a multiple shooting approach is used. This means that we will not eliminate the state variables, and we will consider the state equations as additional constraints to our optimization problem. And the states are simply independent variables, which we also have to optimize over. And so what this does is, in our network, I've made these little springs, which denote the constraints. So we want x1 to be equal to this nonlinear function, etc. And you go all the way to the output of the network, and you see that the output of the network is actually a a simple nonlinear function of the activation at the final layer. So you've kind of decoupled the nonlinearities through the entire network into a sequence of smaller nonlinear constraints and a simple nonlinear cost function. Has been observed in the control community is that this allows to evaluate the cost and the constraint gradients in parallel, and that in some cases the convergence is improved when you have an ill-conditioned cost, as for example in this vanishing and exploding gradient example. So a bit more formally, I've written down what the formal problem is that we want to tackle. So we have our dynamics. So we want to view training as an optimal control problem with n stages with the following dynamics. And now I'm using big X notation, which is that we just simply stack the different data points. I mean, for each input-output data point that we get, of course, all activations are additional variables. So you have these additional variable matrices. And then if you do this, then you get the following problem formulation, where you want to minimize a mean squared error cost, additionally a weight regularization term, and subject to the constraints, which are our dynamics here, and of course that our initial state is equal to our input data, basically. So A is our input data matrix, and Y here is our output data matrix. Well, then optimizing over matrices, it's a bit awkward, this notation. Usually we optimize over vectors, so I'm going to simply stack them now into simple vectors so that the cost and the constraint from before can simply be represented by, we have our cost function here, which is an MSE cost, dependent only on the activation at the final layer and the weights of the final layer. And you have our weight regularization term, and we have our constraints. And this is the constraints that the state at the activation or the state at a certain layer should be equal to the nonlinear function of the previous state and the activation function. So under this lens, we basically end up with a simple equality constraint nonlinear program, right? So we want to minimize some functions subject to equality constraints. I've mentioned some other properties here, like a proper lower semi-continuous lower bounded function. Well, what does this mean? I think in general, this is not something we really need to worry about in neural network training. For example, our cost function has to be proper, so it cannot go to minus infinity. This is quite obviously, it holds, for example, in the cost function we have here, it's lower bounded by 0, right? Because you use positive terms here. So it will not go to minus infinity either. And in our case, we have a continuous function as well. But in general, ALM schemes, which we'll use in this presentation, can deal even more difficult cost functions. So you could come up with more difficult situations, but in this presentation, you usually just simply have continuous lower bounded functions. And then in the locally Lipschitz equality constraints, well, you just need locally Lipschitz activation functions for this to hold. So this is all the typical activation functions will satisfy this as well. Well, the work that I'm presenting now and the ideas up to this point, it's basically what is referred to in recent literature as auxiliary variable methods, where the auxiliary variables, as they call them, are the additional state variables from the control community. And then what is, for example, done in literature is that they use a quadratic penalty cost function to deal with the equality constraints and then apply block coordinate descent, which is like you will separate our total decision variables, which include the weights and the states, and you will iterate between both. This is done the work of Correa and Perpignan, which is like the first work introducing auxiliary variable methods. Then this idea was further worked on in some other papers as well. For example, the activation functions are efficiently dealt with as biconvex constraint in this work. And another interesting idea is to solve the problems emerging in neural network training using ADMM, which allows to highly parallelize the different steps. And finally, some recent work has tried some exact penalty methods as well. And in this work, we will follow the approach based on a conference paper submitted last year to the CDC conference. So it's a control conference, basically, where we address the optimization problems using the Augmented Lagrangian method. And then we will solve the inner subproblems using Gauss-Newton and use forward dynamic programming to obtain the Gauss-Newton directions efficiently. Okay, so first, once again, some additional information. We are going to use the Augmented Lagrangian method for solving our equality constraint problem emerging in neural networks. And the Augmented Lagrangian method is actually quite closely related to the quadratic penalty method. What happens in the quadratic penalty method? This will give you more an idea about what the Augmented Lagrangian method does as well. So in the quadratic penalty method, we will simply take this constraint and throw it into the cost with some penalty parameter beta k. And we will simply keep increasing it all the way to infinity. And then as it increases, of course, this term should go to 0. That's the main idea. So to illustrate this, I've come up with a little toy example, basically. So we have a simple linear neural network with one linear layer and a single data point, such that you have this simple cost function subject to a single constraint. And I will take simply 1, 1 to illustrate it. So this is what happens in this approach. So we want to minimize our MSE cost and our weight regularization term, and then the penalty term, which would enforce that the activation at the first layer is equal to W times the input, which is 1. So this is our constraint. And in the end, in a normal neural network, you would, of course, have that this is true. And this is the red line, which is here. So if we want to converge the solution, we would expect to converge towards this region where the equality constraint is satisfied. So in the first iteration, where the penalty is still low, you get some solution. But it's still far from the region where the equality constraint is valid. But then we increase the penalty, we get closer, we already go to here, we increase it again, we increase it again, and you see that it converges towards this equality constraint, basically. And our level curves, they become kind of these elongated ellipses. So and as the penalty parameter would go all the way to infinity, then we would converge to the true solution, 1 over square root of 2, where of course you see that this constraint is satisfied. So this is good, this looks good, but there are some issues with this. The main issue, of course, from a practical standpoint, is that increasing a penalty parameter in your software all the way to infinity, it seems kind of impossible, right? You need to keep on going and you have a lot of numerical issues. Your problem becomes increasingly more ill-conditioned. This is what I said also in the previous slide, that you get your level curves of your function become very elongated, which is not good for any numerical solver trying to solve this minimization problem. And you get the additional effect that your approximate minimizer, if you would stop your algorithm a bit sooner than when your penalty parameter is all the way to infinity, you will not quite satisfy the feasibility conditions at all. Therefore, you introduce the augmented Lagrangian, where an explicit estimate of the Lagrangian multipliers is added. So in some sense, the idea is the same as in the quadratic penalty method, but you have this kind of shifted quadratic, which is added, right? Because you have this additional term here, which shifts the equality constraints a little bit, and this will help to exactly satisfy the feasibility conditions. So in ALM schemes, what happens? We want to find first an approximate solution of our augmented Lagrangian. Then we will update the Lagrangian multipliers. And then finally, we will update our penalty parameters as well. We will make them increase or even choose them equal. It's possible as well. So this is the main idea, and this will behave kind of similar to a quadratic penalty method in some sense, unless that you don't have the problem that your penalty parameters need to go all the way to infinity, so you will have less issues with ill conditioning. Then what we did in our work for CDC is alter the ALM scheme slightly by choosing an initial feasible point for our algorithm. We basically can guarantee that the worst case performance of the algorithm is bounded. But in general, I'm not too convinced about if this was actually necessary. We did it, but there might be advantages to choosing initial infeasible points as well. The main reason we did this is because getting a feasible point in the neural network is very simple. You initialize the weights as you would normally do, and then you just propagate through the network to get all the activations corresponding to these initial weights. And then you have your initial feasible points. But I think this is not really necessary. You can use any augmented Lagrangian methods for this purpose. But the algorithm just presented here is inspired by the work of Kapila and Yuan. The only thing we added is changing the penalty update rule, because they let basically their penalty go all the way to infinity, which is something we want to prevent, as mentioned before. So this improved our performance in practice a lot. Okay, so now we have shown this ALM scheme. I'll show this simple one again. So this one, but this is still very abstract. How will we solve our inner minimization problems? And that's what I will deal with now. So in the MSE setting, which I was explaining before, we basically want to solve the following problem, where our augmented Lagrangian consists of the MSE term, the weight regularization term, and then the additional ALM terms, basically. And as you can see, this is a traditional nonlinear least squares problem. And to solve this, classically, Gauss-Newton methods are used, where you want to find the Gauss-Newton direction and then apply the standard line search to guarantee that it actually converges. So this is also what we will do. And to find the Gauss-Newton direction, you want to linearize your H functions, which are basically our activation functions here, around the current iterates. So by doing this, we get the Jacobians here in A and B, and we get our additional remaining terms. Basically, if you would write this down, you would end up with this formulation where you would go from here, our original formulation, you linearize it, and then you simply end up with this kind of cost term, where you have this weak coupling between the decision variables, because the activation at a certain layer is only like coupled with the activation at the previous layer, and you get a large sum of these terms. What's the advantage here, now that we have gone all the way to a linear least squares problem, is that we have a closed form solution. From this problem, you know that there's a unique closed form solution, which you could completely compute in a single line of code, for example. What we will do is try to exploit the weak coupling between the variables, and for this we will use forward dynamic programming. To illustrate this, I mean, the main idea is to split this sum optimization problem into a series of simpler subproblems, where first you take the subproblem at the first layer, only dependent on the weight at the first layer, and then you get an entire sequence of optimization problems, where you can see that if you would plug them into each other again, basically, you would get that this bottom optimization problem is completely identical to the one here at the top. So this allows to use a recursive procedure. So you would first solve the first problem, then the second, then the third, then the fourth, all the way to the final one, and use this recursive procedure to obtain all our decision variables that we want to obtain. I will not go into full detail about the entire scheme because it's a bit elaborate and sometimes tricky with the notation, but I will consider like the first subproblem. So this first subproblem is very simple. Would consider the first order optimality condition of the subproblem. And then you have that the weights at the first layer are equal to this if you have a current iterate in the Gauss-Newton iteration scheme. So you would then have this solution, but of course it's dependent on the activation at the next layer. So you plug it back in, and you get that your value function is of this form. Okay, so you have v1 star, and you get that it's some kind of squared norm term here. Okay, and then you can continue with the second problem, because now you can fill this in into the second series of problem, basically, and you can solve the second problem. You can keep on doing this recursively. So that's the main idea. And the interesting thing is that by continuing this procedure, it follows that basically at every layer, the cost, or this value function, as they call it, has the structure as it had in the first layer. The only thing that changes is the matrices and these vectors here. So they need to be updated. So this actually gives a quite interesting scheme then. Well, I see here this term CJ. You can omit it because they will not influence the values of your optimization problem. So we don't really compute them. So the main scheme in this forward dynamic would be simply a forward recursion where we compute all these matrices and all the value functions. And then you have a simple backward recursion where, using the matrices you have obtained, you go back to compute all the values. And that would be like the forward dynamic programming scheme that we have obtained then. And in some sense, it's very similar to the Kalman filter updates, because what you have in a Kalman filter as well is you have some vector, which is like the average of your current estimate, or this is like your current estimate, and you have your matrix, which is like the covariances, and they also would propagate over time. So once again, you have this strong connection between this forward dynamic programming scheme and the Kalman filter from optimal control. So this was the main idea that we applied in the paper. And you end up with this scheme. And of course, it looks kind of nasty, but the main steps, of course, are once again computing this M matrices and these Q variables, which are the matrices and vectors in the value functions. And then we have a backward recursion step where we compute the state, the state variables or the activation values and the weights in a backward recursion step. So now the main question, of course, is what kind of computations are we dealing with here? Is this efficient? Is it not efficient? We need to solve linear systems, for example. Well, yeah, we need to compute matrix vector products. Let's say this is efficient, especially because many of these vectors of these matrices will be sparse. But we also need to solve sparse linear systems, and this is, of course, the most computationally heavy part. And to alleviate some of this work, we have computed the Cholesky factorization of some common terms in our scheme, so that every time that we have to solve a linear system, we only have to do forward and backward substitution steps. And this greatly helped in improving the performance of our method, such that we can effectively get the Gauss-Newton directions in an efficient manner using the forward dynamic programming scheme. Now, onward to some numerical results, although it's kind of a simple toy example that we have designed here. So we have implemented our method in Python using SciPy and the Cholmod library, where the Cholmod is like the library for computing our Cholesky decomposition of our matrices. And then we generated training and test data for a 3-layer network with 250 data points. And then you add some arbitrary noise to it. And the typical performance of our algorithm is actually quite interesting. So what happens in our ALM scheme? So you have an outer ALM scheme and an inner Gauss-Newton iterations, basically. And you see that in the first Gauss-Newton iterations already, the loss decreases tremendously, while in these final iterations, this remains relatively stable. So let's say you have come very close to the optimal loss. But on the other hand, it's in these final iterations that the feasibility converges all the way to machine precision. So in some sense, this is what you would desire, right? This is, you want your loss to go down as fast as possible, while this feasibility, well, you can kind of stop, for example, a bit earlier, because this feasibility, you only need the network weights in the end, right? So this inspires you to stop a little bit sooner, and this is a result we were very happy with to see that this is the case. So when training a 3-layer network with our method compared to ADAM and SUG, we get kind of similar results in the setting that we are looking at here. So the training MSG is kind of similar to ADAM. It's, I would say, a little bit better than stochastic gradient descent in this example. And the computation times are similar. But there's still some things I will mention about the computation time of our method, which will be addressed in future work. Yeah, so onward to the conclusion already. Yeah, we have introduced neural network training and how it can be interpreted as an optimal control problem, and presented a novel ALM algorithm to solve them, where we solved the Lagrangian subproblems using Gauss-Newton. And we proposed an efficient forward dynamic program procedure for obtaining the Gauss-Newton directions. And I think all in all, these approaches, like the one presented in this presentation, are very promising and should be investigated more in literature. And I think that in recent years, it is coming up more and more. So it's a highly, it's an interesting field to work in right now. Regarding the one that I presented in this work, there's still some issues with the scalability. I've mentioned in our example, for example, that we are at 250 data points. But the thing is, we just use all 250 data points. So we have to introduce activation variables at each layer for each data point. So it's, as the number of data points increases, this is not very good. So of course, it would be much more interesting for the method introduced here to also use minibatching, as in stochastic gradient descent. And another thing about the forward dynamic programming is that you end up with a forward recursion step and a backward recursion step. And this does not really allow for a good parallelization, I think. So if I were to continue on this work, I would definitely think of other ways to solve the Gauss-Newton problem. It's still I mean, these inner problems are still sparse linear least squares problem, and there are other ways of solving this efficiently as well. So if you would want to use this for very deep neural networks, it might be more interesting to avoid a forward dynamic programming scheme and try to exploit the sparsity in some other way. And that is the end of my presentation. I hope to get some interesting questions if you have some.
Okay, thank you, Brecht, for the presentation. I hope you can hear us again.
Yes, I can.
Perfect, because we muted the room. Do we have some questions from the room and or online?
I have a question.
Okay, so Davide has a question.
So you said you're solving a system with sparse matrices, but if I remember correctly, so those matrices are defined as you have like matrix products and stuff like that. So they can get dense pretty fast, right? Those MJ.
Which ones?
The MJ matrices in your algorithms.
Ah, yes. Okay. Yes. These ones.
Yeah. So, and you need to solve in a system with those, right?
Yeah. Exactly. Yeah. So you need to solve linear systems with mainly the MJs. Basically, also with these SJs. I don't really mention this, but this is more explained in the paper. So this is why I factorize also this term, because we will not actually compute this SJ matrix, but we will once again solve linear systems.
Yeah, but those matrix products, they can fill up the sparsity pattern of the matrix pretty fast, or not?
Yes, but all these matrices are quite sparse as well, and they scale with the number of data points linearly. So the dimension of these matrices becomes very large, and it's more efficient in practice to use a Cholesky decomposition, because you need to do this multiple times to solve these linear systems. Yes, basically you need to solve this linear system with MJ, and then when using this S matrix, you once again need to use the Cholesky decomposition of M basically internally. Does that answer the question, or?
Fine.
Okay, we have a question online, maybe first from Antonio.
Yes, hi. Thank you for
Yes.
the super nice talk. I was just wondering, why are you implementing this in SciPy and not in one framework like PyTorch or TensorFlow? What is like the just the availability for the solver, for the Gauss-Newton solver? What's the technical issue, if there is a technical issue for that?
A technical issue?
Yeah, so let me first recall the question for the people in the room. So the question was roughly, why are you using SciPy instead of established machine learning frameworks like TensorFlow, etc.?
Yeah, in the end, why I did it, I think it's because of this this connection with the Colmod library to get Cholesky decompositions. This is not something that PyTorch supports. And on the other hand, I was not that experienced with PyTorch to implement it. I think PyTorch, of course, is very efficient for many of these operations, but with this Cholesky decomposition, it did not really seem easy to perform, or at least not for me. So that's one of the reasons why I didn't do this.
Okay, that's interesting, because I thought that someone must have done a Cholesky decomposition in PyTorch or TensorFlow, but okay, thanks.
Yeah, especially a sparse one, right? We want to exploit the sparsity. I think perhaps there is a Cholesky decomposition.
Sparseness is an issue. I mean, I totally agree. There are no real clear efficient mappings of sparse problems to the GPU. This is true.
Yeah.
Yes, and then we have another question from the room. So from Valeria.
Okay, so you showed that you have a cascade of computations, especially for approximating the net series, the inference xj's. And so what about propagation of accuracy? So you somehow solve each problem in accuracy, and how does this affect final xn that one that you use to minimize the loss function?
Okay, maybe I will recap the question in case
Okay.
you didn't reach online as well. So basically you have this cascade, these recursive solves that you perform, but then each of them is solved inaccurately, so of course not to full precision. And the question is, okay, but how does this affect like your final results, that you have this cascade of errors, this propagation of errors as well?
Yes, I think that's also interesting. You would hope that, of course, it doesn't influence a lot at all, because in general, this entire scheme, you want to solve this problem, and you could simply write it as a single linear least squares problem, and then you could get the entire solution using a single operation with an extremely large matrix, like like this, and then you have like a lot of smaller submatrices, and all these submatrices is what I use in all these computations. I try to avoid having a very large single problem, and I split them into a large subset of small problems. Basically, this is what this forward dynamic programming does. And you would hope, of course, that the error propagation is not worsened by that. But the conclusive answer, to be honest, I don't know if it is the case.
So is this a hope, or is this truly the case, is the follow-up question?
I would not know. I don't know the answer to this. If it is better or worse to solve the problem directly or to solve the sub-problems. Yeah, personally, I don't know this.
Okay, thank you. Do we have any other questions here or online? There's a raise hand feature, of course. If not, then we have another question by Ignas. We cannot currently hear you, Ignas. Your microphone does seem to be unmuted, but it doesn't seem to register sound.
Okay, you said something in chat as well.
Yes, feel free to type the question, of course.
Yes, so I mentioned parallelization indeed.
Yeah, so the question is, what about parallelization, and on which level do you mean, like where the parallelization can be applied, I assume?
So there are some approaches, I think mainly the one, I have to go back a lot in the presentation now. I think the ADMM approach from Taylor, this is an interesting one to take a look at if you're interested in this. Because in this scheme, you can parallelize between the different steps at the different layers. And this would allow, I think Taylor mentioned this in his paper, like at the moment, a lot of people parallelize over GPUs, for example. Maybe in the future, you can perform more computationally heavy steps on parallelized CPUs. And in this case, it might be interesting to perform more difficult steps. And then his steps are completely parallelizable over CPUs. So this is one of the ways that would be more interesting. But in the forward dynamic programming procedure, there's no possibility to do this because you're kind of stuck with going forward first and going backward afterwards, which is inherently sequential, while you would want to parallelize over basically these coupling terms over the different individual layers.
Okay, so Ilya says, okay, perfect, thank you. Do we
Okay,
have any
thanks.
other remaining questions? If not, in that case, we would like to thank the speaker again for the very nice and interesting presentation.
Thank you.
So right now we will have a break, I think about 15, 20 minute-ish break with some coffee. I hear some pastries to take as well. So you're all welcome here in Bologna. If not, you will need to provide your own pastries. And hopefully we will meet again in about 15 to 20 minutes. Yeah, all right, thank you.